Okay, so today we're going to talk about resistance, resistivity, and Ohm's law. Uh, the last lecture we had, we introduced this idea, this concept called conductivity, and we talked about how that related to various material properties in your wire, your conductor, what have you, like the mean free path for the electrons that are moving around, the number of electrons per unit volume within the material, and things like that. And we gave it the symbol lowercase sigma, and found that it was related to a quantity called current density, which is current per unit cross-sectional area, and the electric field running through the conductor over which that current density is flowing. And at the end of that, I said that this relationship here is a form of what we'll come to know as Ohm's law. And we'll get to that in a moment. So we can play around a little bit algebraically with this and restate it very briefly, like so. Just getting the field on one side. And we have the inverse, the reciprocal of conductivity over here, which we get to assign that its own name. The reverse of conductivity, what makes it harder for a material to be conductive of electric current, we call this quantity resistivity. So we define resistivity we use the lowercase Greek letter rho, and that is the inverse of conductivity. I'll stick that over here for keeps. And then, as a reminder, since we have a fine collection of variables with the same symbols meaning different things, we've used rho before to indicate density, volumetric density, charge density. In this case, it's a quantity called resistivity. We've used sigma to indicate surface charge density. Here it's conductivity. Hooray for context. So we can go ahead and take this. And we want to relate this not to current density, but to current. And we want to relate our E field not to, we want the other side here not to be related to the E field, but rather to the potential difference. So that if we have some wire, what have you, that has some field within it, and you have your current density flowing through it, it's also going to have some potential difference across it. And this section of wire may have some length to it. We'll call that length lowercase l. And we know that potential difference is related to the E field through a line integral. So we have, we recall that potential difference is the line integral of the E field with respect to position, the negative thereof. So we're going to go ahead and set this up, and we're going to integrate both sides from some position 0 to some position L. And we get resistivity here, our current density, which is overall current divided by the cross-sectional area, and all of these we'll consider to be constant across that length. And so our integral on the right-hand side, we're just going, we're just integrating across that length itself. So the right-hand side is just simply rho L over A times I, where A again is the cross-sectional area of our wire. If we made this more of a (3D) thing. And then we have our potential difference here. This is the negative potential difference going through that. It will have a negative value. But I'm expressing it as a positive value here. The integral would, we know, is going to give you a negative sign there. That's how much potential drops going through something of length L with that resistivity. But I'm going to express it just as the size of it for now. So we have that, and this quantity here, we get to assign its own name. We can see that the bigger this thing is, the more potential it takes to drive the same current. It's going to, if that's bigger, there's a greater resistance to pushing the current through. So we define this thing as resistance. We say, okay, R here, that's resistance. And relating to the material properties, it's this resistivity, which is dependent upon the substance, and then the dimensions, the L over A. But we also define it, this is how it's measured, but it's defined rather in terms of the potential difference and the current. So it's the ratio between the two. And this here is Ohm's law in the traditional derivation. So I'll stick that over here as well. So, or V equal IR. So it has units, then our units, here let me increase this thing here. So our units of resistance, our units of potential over units of current. So those are volts per amp, which we call ohms, as in Ohm's law, and we use the symbol capital omega to represent those units. Ohm's law is named after a fellow by the name of Georg Simon Ohm, and he published the law and his studies of electric current in 1827, having done the work the previous couple of years leading to it. So why do you have resistance? Well, we talked about that as being related to, well, how many free electrons do you have that can move around through your material? And it also turns out that, well, you're going to get, we can see that it's going to get bigger as the length of your resistor gets longer. So I have here a variable resistor, or a rheostat. And the way this thing works is that if you want to send current across it, you could send it across the whole coil here by connecting between these posts. Or instead, we see that there's a connection point here across this low resistance, high conductivity bridge, so that if you hooked up over here and here, then wherever this slider was placed, it would have to go through all of this coil and then could jump up to the slider and across. So that if you have it all the way over here, you have a lot of resistance, a lot of length to go through, and then slide it way up here and you've got pretty much no resistance, just about, as it goes through this big fat conductor, large cross-sectional area, low resistance. So very little resistance through that. You can imagine if you have this thing hooked up to a light bulb, and you had it hooked up so that you had this slider all the way down here, then it would have to go through a lot of resistance before getting through. That would leave a lot, it would take away a bunch of the potential. You would be pushing a lower current through your bulb, and you would get a dimmer light. But if you bring it up here, it's a shortcut, doesn't run into all that resistance, and you've got a bright light. This is effectively a dimmer switch, a variable resistor. This is basically what's sitting behind all the dimmer switches that you've got that are sliders. It's pretty much all of your electronic controls that are slider based have this sort of configuration going on behind the scenes, where you have a variable resistor set up there so that it allows varying amounts of current to pass through because you're increasing the resistance as the thing goes along. If you have it in a dial instead of a slider, it's just the thing wrapped up into a torus, like a donut, instead. So that's where that goes. Now, let's see. So let me stick resistivity here and relate that to resistance, and give us a little more space to work with again. So we were talking a little bit about resistance and relating to what's going on at a micro level inside your conductor. And you can imagine then that if you've got your conductor and you have all your little electrons that are trying to whiz around, and they've got all of these positively charged nuclei plus inner shells sticking around, that the electrons, they're bouncing around here and they're interacting, and these nuclei and inner electron shells for your atoms are basically like the target size for these things to run into. They get closer to them, they're going to be subjected more to larger amounts of those forces. They get slowed down more. The bigger the target, the slower it goes, the bigger the resistance. Well, if you had a higher temperature, then the random motion of the electrons are increased, but also the random motion of your targets get increased as well. And so the faster they're vibrating, the higher the temperature of the material, the more time the drifting electrons spend interacting with them, the bigger the resistance they get. So resistivity, it turns out, has a temperature dependence as well. Now this is observed. This is not like a theoretically constructed thing that's based on fundamental theory for the rule that goes with this, but rather it's based on observations. And we see that it's proportional to some base value at some particular temperature, often taken at like 20 degrees C or something like that. Plus some amount that increases as the temperature increases. This alpha is a constant. Here's our delta T for temperature, in like degrees C or what have you. So this is just like the resistivity temperature constant. It depends upon the particular materials that we're talking about. And whenever you see one of these linear relationships in physics as a physical law, you can guess that it's an approximation. We're making like a first order approximation here, where you can, as you observe it in the real world across all temperatures of the material, as long as it's in the same state of matter, it's probably a bit more complex than linear, but it probably also holds pretty close to linear for a good long temperature range. So that's going on there as well. There's another topic here that we see with current flow, and that's the amount of power that it takes to push a current through a resistor or across a potential difference. How much power is dissipated within the resistor as those electrons are bouncing around and interacting with all the material inside. So what do we get with that? Well, we know that power, by definition, is the rate of change of energy within the material. It's the time integral of effectively the time integral of the work done on the material. So it's, when we're talking about potential differences, that's the time integral of the charge times the potential difference. Well, the potential difference for some particular length of wire can be held to be fairly constant. So in that case, we pull the delta V out, you get dq dt, which is current. So the power dissipated then is just I delta V. We can express this in other ways as well. When you have Ohm's law here, you can take that and substitute that in, and we get power goes like I squared R. So if your current is held constant, you dump more power into it, the bigger the resistance. Or you can express it, you can substitute out the current so that it's just in terms of potential and resistance. And you do that, it's delta V squared over R. And the type of energy that's dissipating with this power by pushing the current through your resistor is thermal energy. You're increasing the temperature. We call this Joule heating. Let's see. After James Prescott Joule, the same fellow for whom the unit of energy is named after, based on some experiments that he had done, theory work that he did in around 1840-ish. And this is the same thing that's behind your electric range, your electric toaster ovens heating, electric heaters, incandescent light bulbs, and heating up the filaments for those. It's all through Joule heating. It's all dumping power out I squared R, or delta V squared over R. The potential across your light bulb relates to the power and the current through it relate to the power in the rated watts across the thing. That can tell you what the resistance of the thing is. No matter what voltage you have it hooked up to, if it's not hooked up to a standard wall outlet. So let's see. And that is where we're going to end for the moment. Oh, one more thing. I brought this rheostat up here earlier, and this beast, as big as it is, as long as it is, it's got a resistance of 10 ohms, which is kind of small. We can have resistors, 1,000, 2,000 ohm resistors, that are the size of a pencil lead. So, why? Well, you make the thing big because you're going to put some set potential difference across it. You can control the potential difference. That's easier to determine ahead of time than the current. So the power that goes through it in the form of thermal energy is going to be inversely proportional to that resistance. So if you have a small resistance, that's a lot of power for the same potential. The thing's going to heat up. You stick this thing into the size of one of the resistors, or this amount of resistance into the size of one of the resistors that you've got sitting in your cell phone, that thing's going to smoke. Right. So there we go. All right. That's it for this lecture. See you the next time.